Our monthly webinars are based on our technical reports, which are available from our website, IEACCC.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration. The subject for today's webinar is Carbon Capture and Utilization, also known as CCU, presented by Dr. Qian Zhu. The report on this topic will be published in August. I'll now hand you over to Qian.
Thank you. Good afternoon, everyone, and welcome to the IEA Clinical Centers webinar. Today, I will review the latest state of development on CO2 utilization technologies, or CCU technologies, and discuss the environmental impact of CCU. I will begin with a brief discussion of the possible uses of CO2 and the technological pathways to convert CO2 to marketable products, which is followed by a review of the latest status of CCU technologies. I will then discuss the environmental impact of CCU in terms of the supply and the demand of CO2, the life cycle analysis of CCU products, and the role of CCU in climate change mitigation. And finally, I will close the webinar with key messages. As shown in this figure here, the CO2 has many possible uses. It can be used directly, such as EOR, making fizzy drinks as a coolant, and etc., or indirectly by conversion. CO2 can be converted into a wide variety of commercial products, such as chemicals, either as a final product or intermediate, synthetic fuels, construction materials, and polymers. Currently, there is a considerable interest in the use of CO2 to grow microalgae and the potential of algae to produce biofuels, chemicals, and other products. My study focuses on the indirect CO2 use by conversion of CO2 to value-added products via chemical or biochemical reactions. Due to the large and varied wealth of R&D, this review will focus on the CCU technologies that have reached commercialization or pre-commercial stage or close to large-scale demonstration. CO2 is the most oxidized form of carbon, and it is an extremely stable, low-energy molecule. As a consequence, high temperature, reactive reagents, and energy are in general required to enable a reaction with CO2. This makes CO2 conversion processes economically unfavorable. To overcome this, suitable catalysts are used. Efficient and selective catalytic systems are the core technology for the successful and economical use of CO2 as a chemical feedstock, and have been one of the most sophisticated and complex R&D area. There are many technological routes to convert CO2 to commercial products. These include catalytic, electrochemical, mineralization, biological, photocatalytic, and photosynthetic process. The electrochemical conversion of CO2 has been a dynamic field of research. Many possible routes for conversion of CO2 to products such as syngas, methane, methanol, or dimethyl ether with incorporation of renewable power in the production process are being explored. Various technologies have reached a semi-commercial stage of development with possibility of shortly being commercialized on a large scale. Others are ready or close to pilot scale demonstration, whilst many more are in invention and concept validation phase. For example, a German company, Sunfire, has developed a process using high-temperature co-electrolysis of steam and CO2 to produce syngas. The syngas is then converted into synthetic fuels such as gasoline, diesel, and methane. A pilot plant in Dresden, Germany, successfully produced its first batches of high-quality diesel fuel in 2015. In July 2017, Sunfire announced that it had begun engineering of the industrial-scale power-to-liquid production facility in Norway, which is expected to be operational in 2020. The 20 megawatts power input power-to-liquid plant will have an annual production capacity of 8,000 tons of long-chain hydrocarbons known as blue crude. Another German company, E2Gas, developed a process that reacts CO2 with hydrogen generated by water electrolysis to form methane. The direct coupling of a PV power generator with electrolyzers has been successfully demonstrated in different power ranges. E2Gas built a power-to-gas plant with a 6 megawatts power input in Germany for the automaker Audi. The plant has been producing Audi's e-gas since 2013 in a dynamic and intermittent operation using wind power and CO2 from a biogas plant. In 2016, a Japanese company, Hitachi Zosen Innova, acquired E2Gas technology. In December 2017, the company, together with its parent company, Hitachi Zosen Corporation, was awarded the turnkey contract to build the first power-to-gas pilot plant in Japan. The plant will take fossil fuel CO2 emissions and combine CO2 with hydrogen to produce methane. The methane is then fed into the existing gas grid. Hitachi Zosen Innova will provide the E2Gas catalytic reactor for the methanation process. The pilot project is scheduled to be commissioned sometime in between 2018 and 2019. Other technologies such as Haldol Topsoe's CO2 to syngas or methane process, DNV's EC-form reactor that converts CO2 to formate or formic acid, and the technologies developed by former Liquid Light to convert CO2 to various chemicals are ready for pilot or large-scale demonstration. The photocatalytic or photothermal catalytic conversion of CO2 is another area that attracts an increasing research interest worldwide. A notable development is the working prototype of sunshine to petrol reactor recently demonstrated by the Sandia National Laboratory of US DOE. The heart of this process is a unique metal oxide-based thermochemical heat engine called CR5, which features a continuous flow, spatial separation of products, and thermal recuperation. However, research in this field in general focuses primarily on the development of effective novel catalysts with high energy efficiency, high yield, and high selectivity, and the reaction mechanisms at laboratory scales. The prospect of any process reaching the productivity necessary for a possible exploitation of the technology at present is very low. Process for catalytic conversion of CO2 to methanol or other fuels via different routes have been developed, and some are in pilot scale demonstration or pre-commercial stage. Atlantic CRI developed process consisting of CO2 production by electrolytic cracking and the catalytic synthesis of methanol. In 2012, CRI commissioned a CO2 to methanol production facility with a current capacity of 5 million liters per year. The plant now recycles 5,500 tons of CO2 per year. CRI and a consortium of European companies and research institutions have been awarded 11 million euros under the EU's Horizon 2020 program to implement CRI's technology in the Swedish steel plant to demonstrate how residue blast furnace gases can be converted into liquid fuel. A Canadian company, Carbon Engineering, has been developing an air-to-fuel process that combines direct air capture technology with water electrolysis and fuel synthesis to produce liquid hydrocarbon fuels. In December 2017, a pilot plant had produced its first small quantity of liquid fuels. The German company BSC Engineering has been working to develop a process for producing methanol from CO2 and hydrogen using renewable energy. It envisions the first rollout of a 10 megawatts power-to-methanol plant in 2019 to 2020. Several interesting bioconversion routes using CO or CO2 are also under development, some at industrial scale, such as the LanzaTech fermentation process for ethanol production. LanzaTech's process uses microbes that grow on gases to transform CO-rich waste gases and the residues into useful liquid commodities in a continuous process. LanzaTech started ethanol production in 2008 at its pilot facility in New Zealand, which is linked directly to a steel mill's off-gas exhaust. During 2012 and 2014, LanzaTech commissioned several demonstration plants in China, Japan, and the USA, producing ethanol from CO-rich flue gas from steel mill, municipal solid waste-derived syngas, and the syngas from biomass gasification, respectively. The first commercial facility located at Jintang Steel Mill in China converting emissions from steel production to ethanol with a capacity of over 60,000 cubic meters per year, just began operation on 3rd of May this year. And several more commercial plants are planned or under construction in China, Belgium, and South Africa. For conversion of bioconversion of CO2, interesting developments are also in the area of engineered bacteria and enzymes, but these are still in the early stage, small-scale experiments. The developments of technologies for producing construction and other material through CO2 mineralization are more advanced. Several companies are now providing commercial systems for carbon-cured concrete and other carbonate material production. CO2-cured concrete has properties similar to or better than those of traditionally produced concrete and can store CO2 permanently. These technologies are easy to be installed or retrofitted in the current production systems and are economically competitive with relatively low costs. Therefore, they are expected to be one of the first CCU technologies to achieve widespread deployment. For example, the process developed by company CarbonCure has already been adopted into a number of plants owned by several producers, with 25 machinery installations and 45 ready-mix installations, mainly in North America, and there are plans to retrofit more. Solid industrial waste, such as steel slag, cement kiln dust, waste concrete, and coal fly ash are generally alkaline, inorganic, and rich in calcium and magnesium, so they can be used to produce construction materials by carbonation. Often these materials are available at emission sources already appropriately sized. Various processes to convert industrial waste to cementitious materials, aggregates, and other building-related materials via carbonation have been explored. A British company, Carbon8 Systems, developed accelerated carbonization technology, ACT, that uses captured CO2 as a resource to treat a wide range of thermal wastes, such as cement dust, steel slags, oil shale ash, incinerator ash or paper ash, and the contaminated soils. The first ACT plant started operation in 2012 in Suffolk, UK, and it now produces over 65,000 tons of carbonated lightweight aggregates per year from municipal solid waste incineration residues. In 2016, a second plant with capacity of 100,000 tons per year was commissioned in Avonmouth, and 3 more UK plants of a similar size or larger are expected to be operational by 2018. CO2 mineralization process for manufacturing inorganic chemicals have also been investigated. The SkyMine process, developed by a US company, Carbon-Free Chemicals, both captures and utilizes CO2. It can remove CO2 and acid gas such as sulfur dioxide, NOx, as well as heavy metals from exhaust gases from power plants and other industrial processes and transform them into marketable products such as baking soda, caustic soda, and bleach. Researchers from University of Aberdeen is developing a carbon capture machine that directly dissolves CO2 in flue gas from stationary sources into dilute alkaline solution, converting it to carbonate ions with efficiency approaching 100%. The carbonate solution is mixed and reacted with readily and abundantly available calcium and magnesium brines to selectively precipitate calcium carbonate and magnesium carbonate, which have commercial values in existing and new markets. These processes are yet to be demonstrated at large scale. Significant advances in the copolymerization of CO2 with epoxides to form cyclic polycarbonate or polyols have been made. Various companies are exploring this route, with some processes are already in commercial operation and others are close to demonstration or commercialization. For example, Japan's Asahi Kasei has its first commercial plant in Taiwan in 2002, and several more plants in South Korea, Russia, and Saudi producing polycarbonate using the waste CO2 from ethylene oxide production process as a feedstock. Covestro has been producing polyols for flexible polyurethane forms since 2016. The plant has an annual capacity of 5,000 tons, and the CO2 processed is a waste product from a neighboring chemical facility. The U.S. Novomer has developed a catalytic technology to produce polypropylene carbonate polyols containing up to 50% by weight of CO2. The company's initial production are manufactured at a multi-thousand-ton commercial scale facility in Houston, USA. The U.S. automaker Ford has been working with Novomer to develop foams and plastics using Novomer's polyol for applications such as seating and other parts of for the Ford cars. The CO2 savings of CCU depends largely on the utilization option. It is necessary to apply sound analytical methodologies to assess and estimate the full range of benefits, such as the net CO2 emission avoided, the duration of the CO2 storage in the product, and the potential market value of its use. Many CCU technologies are under development, and the data required are not yet available for a full life cycle analysis. Nevertheless, several LCA have been conducted for different CCU processes based largely on assumptions. These results may not be accurate and reliable, but they could provide some indicative comparisons. The table on the right shows the LCA of concrete made using carbon kiln process. The result is circled in the red, which shows the CO2 killed concrete has a net CO2 emission reduction by approximately 18 kilos per cubic meter of concrete made. The figure on the left compares the LCA results of several CCU processes and the CCS in terms of global warming potential. The researchers collect the 16 LCA studies and recalculated the results for comparison purpose. It can be seen that most of the CCS, CCU processes have environmental benefits except for the CCU product derived from algae, microalgae production. In general, the results indicate that CO2-derived polymers or CO2-killed concrete have better environmental performance and a smaller carbon footprint than those traditionally produced counterparts. The LCA study of CO2 to fuel suggests that liquid fuels such as methanol production from CO2 have environmental benefits if the renewable energy is used for the production. The potential global supply, CO2 supply is estimated to be more than 12.7 gigatons per year, whereas the current CO2 consumption is estimated to be just over 0.2 gigatons per year. It is not expected to see a drastic increase in CO2 demand in the near future. So clearly, CCU by itself cannot be the solution for climate change mitigation. Besides, most CCU products, such as liquid fuel, only store the CO2 in the product for a limited time, perhaps a few months or a year. And when the product is used, the CO2 will be released back into the atmosphere. Moreover, conversion of CO2 into, for instance, methanol requires large amount of energy. For CCU to be carbon neutral, the required energy must be provided from renewable energy sources. However, excess renewable power for supplying industrial scale CCU productions is not yet available. So, what is the role of CCU in climate change mitigation? Well, despite all these limitations, CCU has an important role to play in climate change mitigation. At present, the global economy is largely built on fossil fuel use in a linear one-way from cradle to grave production model, and this is not sustainable. Transforming the linear model towards a circular carbon economy, coupled with improved efficiency and the expansion of renewable energy use, is essential to reduce carbon emission and increase resources efficiency and conservation. Closing the carbon cycle by CCU means using carbon and avoiding release of CO2 by capturing and using it again and again, which mitigates climate change sustainably in the long term. CCU provides routes to use CO2 as a valuable carbon source. to substitute fossil fuels and introduce renewable energy into the production processes, allowing transformation of manufacturing industry to new sustainable production systems at minimal costs. In some cases, the revenue generated by CCU can offset the cost of carbon capture and hence provide an economical driver to accelerate the uptake of CCS. More importantly, CCU presents expanded options and reduced costs for climate change mitigation. So, the key messages for you to take home. CCU provides rules to use CO2 to substitute fossil fuels and introduce renewable energy into the production processes, allowing transformation of manufacturing industry to new sustainable production systems at a minimal cost. Therefore, CCU should form part of an overall strategy to mitigate climate change alongside improved efficiency, curtailed consumption, expansion of renewable energy use, and CCS. CCU technologies are rapidly advancing, with some are already in commercial operation and more are emerging in the commercial market. In a short to medium term, CCU will continue its progression, especially in areas that are technologically more advanced, such as CO2-derived polymers, CO2 carbonation, and methanol production. In the long term, CCU will become a key element in the circular carbon economy with sustainable low-carbon chemical and energy production. Thank you for listening, and I'm happy to take some of your questions.
Thank you. We have the first question here. So this is, how far is this technology away from becoming reality?
Well, some technologies are already in commercial operation now, like the co-polymerization of CO2 and the carbon-cured concrete production. They are already in commercial operation, and there are some, production of methanol in small scale, and the development is really taking place rapidly, and we can see, more of the process are rolling into the commercial market in the near future.
Great, and I think we have another one here saying, which CCU technology has the least life cycle impact in terms of CO2?
Well, there are some life cycle analysis carried out, but because most of the analyses are based on assumptions, so the results very largely depends on how the assumptions are made. However, for the polymer derived from CO2 and the carbon-cured concretes, they definitely have lower CO2, can avoid CO2 emissions, has environmental benefits.
And we have time for one more, I think, and it says, what are the estimates for the CO2 demand potentially based CO2 demand potential based on? And are these technical or economic potentials?
These are actually the CO2 already consumed by the industrial processes. It's based on the actual production that consumed CO2.
Thank you so much. This is all we have time for today. Thank you all for joining us today, and goodbye.